let's go ahead and get started. Today, we're going to be looking more on the idea of volume rotation. And also, we're going to look at what happens when we do non-volume, what we call slicing method, non-rotation solids, that we're going to find the volume of. But just want to highlight what we've done so far. Last thing we were talking about was the shell method, and we got through a couple of examples there. So really, this is what I want to kind of focus on here. When to do what, where. So these are your classic formulas. Now, you have what we call the disk washer formula, disk washer method. That is, volume is equal to pi times the integral from A to B of big functional radius squared minus little functional radius squared dx. Now, what is this formula going to give me? This is, since this is the disk washer formula, with that dx right here, this formula is going to be rotating the region about the x-axis or parallel to the x-axis. It's either going to be going around the x-axis or parallel. So it's going to be rotating it this direction. Does that make sense? Now, with that, if I give you volume is equal to pi times integral from C to D of big functional radius squared minus little functional radius squared, but I put a dy on there. That dy tells me that I'm going to rotate the region about the y-axis or parallel to the y-axis. That dy is going around the y-axis. This is the, quote, disk washer formula. Does that make sense? Now, that being said, let's compare this to the shell method. The shell method formula was volume was equal to 2 pi times integral from A to B of what we call a point radius. Use an arbitrary point there. Point radius times f of x top minus g of x bottom. And again, anytime you're subtracting stuff off, you got to put parentheses around dx. What is this shell method formula telling me? This tells me that the function is in terms of x, but we're going to rotate the region about the y-axis or parallel to the y-axis. Okay? So, my function is in terms of x, but the shell method rotates around the opposing axis. Here, the function is in terms of x here, and they're rotating around the x-axis. I want to use the disk washer method. When the function is in terms of x, but I want to rotate around the y-axis, I want to use the shell method. Because to be able to do this these two guys are doing the same thing, but it's based on what the function's in terms of. And I don't want to sit there and have to take my function and to solve for one variable in terms of the other. One, it's a pain. Two, it may be impossible. Because there's lots of equations out there that I can give you that you can't solve for x in terms of y. So, and then, of course, there's this formula here, which we haven't actually discussed yet, but you need to know it. It's the integral 2 pi times integral from C to D of the point radius times f of y right minus g of y left. This will be dy. Catch a pattern of what these formulas are doing. This guy right here, my function is going to be in terms of y, but in the shell format, the shell method will rotate around the opposing axis. So in this one, we're going to be rotate the region about the x-axis or parallel to that x-axis. So there's two sets for each one of these formulas that we're doing, and these are now the big pictures of these things. But the ultimate goal is to not have to manipulate the equation, even if you can or not. You need to know, what's my function in terms of, how are they defining these regions? What axis do I want to rotate around? And from that, you can tell which formula you should use. Don't manipulate the equations if you can avoid it. Manipulating the equations causes careless errors, and sometimes you can do it, and you'll get the exact same answer, the beauty of math. But sometimes you can't even do it, because, you know, y equals x cubed plus 3x squared minus 2x plus cosine of x minus e to the x plus 12. Knock yourself out. Solve for x in terms of y. You won't be able to do it. Okay? It's impossible, because it's not a one-to-one function. So this is the big picture. Does that make sense? When to use what method. So, and the reason why I'm telling you guys this, and again, we'll do some more examples, is I've opened up for you guys, go over here to your Canvas page, and if you go to modules, click on modules, scroll down, we're in, since I've just discussed the show method, that's officially the 7.3 form, 7.3 section. So scrolling it down, you know, we've covered a lot of material, but well, about halfway through. It is about spring break here. So right at the bottom, you see, hey, your next calculator project, okay? But don't worry, it's due later. I haven't decided on that date yet. I just happened to open it up, March 21st. See, when would March 21st be? Let's take a look at this. See, we're off here. We got this. I don't know if it'll be March 21st. It may be a little bit later, but it will not be immediately when you come back from spring break. Officially, I was going to do it here. So I'm talking about probably around March 18th or something or other, but sometime. I haven't decided completely on my date yet. So, but it's open already. So let me click on this thing. Here it is, and let me show you what this thing looks like. So here's a PDF of I may have to go back and fix this thing, because my links may be open, but I'm going to open it up because the computer likes me. This is what your calculator project number 2 looks like. Now, first thing is about using your calculator. Now, there's a shade button. I don't want you guys to use the shade region. I don't care about that. But when we first drew this thing up, it was kind of nice. But that was from the old TI-83 stuff. They had the little shade thing in there. Your calculator's a little more advanced, so I'm not going to worry about shading anything right here. But it's the idea of finding points of intersection and then using the integral, because this is a calculator lab. What does a calculator lab mean to you people? Let me explain. It's a calculator lab. Therefore, you're supposed to use your, all right. So we're going to be doing a lot of setting up of integrals, and we use the calculator to integrate them, okay? So this is going to be really getting into your integration mode on your calculator and stuff like that. So the first little section here is about area. So all these problems right in here are about calculating the area between these two curves over this particular region and stuff. The next section is about volumes, the volume of slices and things like that. So the idea of which method you should use and how you should actually set this thing up and stuff like that. So when you look at the problems, this is what I really want from you guys. So I want you guys to draw the region. I don't want you to manipulate equations. Draw the region, find the points of intersection. Now, if the function is in terms of x and you're rotating around the x-axis or parallel to the x-axis, which method should you use? The first one, okay. Disk washer, right. Disk washer method, okay. Functions in terms of x, rotating around x. If the function is in terms of x, but you want to rotate around the y-axis, what you going to use? Shell method. And all the problems we're giving you here, the functions are going to be in terms of x. And look at what we're doing. We're setting you guys up for the next test and the final exam. They're going to give you one function, this region right here, and they're going to ask you to rotate around the x-axis, rotate around the y-axis, rotate around the line x equals 1, rotate around the line x equals 2, rotate around the line x equals -2, rotate around y equals 1, rotate around y equals -1. One region, and they're making you beat it up. Does that make sense? That's what they like to do. That's what they like to do to you guys on the final exam. They'll give you one region, and they'll ask you to rotate it this way and then rotate it that way. And set up the integral, and then sometimes ask you to evaluate it. Sometimes they even say, hey, use your calculator to evaluate it, okay? So that's what this whole section is about for this problem here, and actually these problems right here. I want you guys to basically use the idea of using shell method or disc washer method. We talk about vertical slicing versus horizontal slicing and stuff like that. What I really want is the idea of disc washer versus shell method. And I may go back and rephrase these words, but disc washer, see, slice the disc washer versus the shell method. So your next calculator project is up and waiting for you guys to play with, but it's not going to be due right after spring break. Don't worry. You guys have enough to go back and study up on. But I will make it probably due the week after. I was just giving you guys, if you're sitting over there in Fort Lauderdale or wherever and bored, you can sit there and do a calculator project. So there you go. All right, so now let's pick up where we left off then. So we did the shell method problem. We did a couple of them. So I want to start with this one right here. It says this. Sketch and find the volume that is created by rotating the area bounded by the curves y equals x to the 2/3 power, y equals 0, and x equals 1 about the line x equals -2. If you notice what they're doing even in the notes, what we came up with is basically we're mimicking what they typically do to you guys on the final exam. We're doing the same region. If you look at the last two problems, it's the exact same region. What does that region look like? It is this one. It's y equals x to the 2/3 power. So it starts at the origin, kind of bows out right here. This is y equals x to the 2/3 power. There's also this part over here in the second quadrant, but my equations always put this stuff in the first quadrant on this one. So y equals 0. Y equals 0 is the x-axis. X equals 1 right here. So cutting it right here, and we're talking about region captured by all three of these equations. Let's talk about this region right here. And now, what are we rotating around? Where's my axis of rotation? My axis of rotation is over here at x equals -2. This is my axis of rotation. So, we're not going to tell you which, well, sometimes we do. But for the most part, we're not going to tell you what method to use. We're going to want you to use the method, okay? Which one is more obvious and logical? My function is in terms of x. We are rotating around something that is parallel to the y-axis. X to x, dishwasher. X to y, shell. That's the deal. Similarly, y to y, dishwasher. Y to x, shell. Opposing axis to the variable, shell method. Same axis as the variable that you have the function in terms of, dishwasher. That's the pattern, and that's what you guys got to get down on this stuff. Does that make sense? So, the function is in terms of x. I got x to the 2/3 power. The axis of rotation is parallel to the y-axis. This screams shell method. That's what you got to get down. Know which method to use at which circumstance. There's only two formats, but you got to know when to use what. So the shell method formula is volume equals 2 pi times integral from A to B of what I call the point radius times f of x top minus g of x bottom of my region dx. So setting this up, this will be volume is equal to 2 pi times integral of the point radius times f of x top. Look at your region. When we talk about tops and bottoms, we're talking about the top and bottom that define the region, and these are the function. F of x is the top, that's x to the 2/3 power. Minus g of x is the bottom. The bottom equation is this is the x-axis, which is y equals 0. Does that make sense? So it's y equals 0, minus 0. dx, the big question is, what is the point radius? Point radius, different from the big R functional radius. Point radius is you use an arbitrary point inside the region. Because this is dx, it will be an x point. And you want the distance between that arbitrary x point and the axis of rotation. So your point radius is a distance. And when you calculate a distance, it's either top minus bottom or right minus left. That's what how you calculate to get a distance out of equations is all about. And again, you'll see this stuff over and over again in Calculus 3. The first thing we start you guys out in Calculus 3 is vector calculus. We talk about vectors and from points to create vectors, end minus beginning, right minus left, top minus bottom. This stuff's going to come back and haunt you. Right, on the right is the region. It is x. Minus on the left is the axis, -2. X equals -2. Of course, I'm going to clean that up, and so what do I get? X plus 2 is my point radius. Now, what about the bounds? Once you've got the bounds, you're done. It's about the region that you're rotating. It's the bounds of the region. Not where you're going, but where the region is. Question? Yeah.
So basically, the point radius is the distance from the arbitrary point within the space we're trying to find to the axis that we're rotating.
Right. And we'll talk about that in the next problem as well, but here's the deal. It's either going to be a number minus x or x minus a number. It depends on which side the axis is on. In this problem, the region is on the right, the axis is on the left. It'll be x minus number. When the axis is on the right and the region is on the left, it's going to be number minus x. And when you get it backwards, you get a negative volume. That's how you know. You get the same answer, the volume will be negative. Oh, I screwed that up. You should look at right minus left, not left minus right. That's what's really going on. Does that make sense? But now, what's my bounds? It's the bounds of the region that's being rotated. That's why I don't want you to draw what we're finding the volume of until after you calculate this thing, because you need a nice clean piece of paper, clean graph of what the region is. Where's the region between? This is dx, so I want x numbers. It's between the origin, which is x is 0, to x is 1, from 0 to 1. Again, this is a problem that you can basically do by hand if you really, really wanted to. But this actually sets up the equation. So when I ask you about set up the integral that actually calculates the volume, this is what I'm after. Now I'm going to use my handy dandy calculator to calculate this here volume. So volume is going to be equal to, I'm turning this thing on, all right. And what do I get here? All right, so first thing, I'm going to hit math number 9. Integral from 0 to 1 of the point radius, which is parentheses x plus 2, close parentheses, times parentheses, x to the 2/3 power, 2/3, John, 2/3 power, minus 0. Now, minus 0 because it was the x-axis on the bottom, close parentheses. Now, if there was an actual function that was on the bottom, don't forget to put parentheses around it. When you subtract off something or other, you got to have parentheses. That negative is going to distribute. dx. The only thing that I was leaving off in terms of the way I'm typing this thing in on my calculator is what? The coefficient in front, the 2 pi. And this is the shell method, so it's 2 pi. And traditionally, we leave the answer in terms of pi. So I got this answer, right? However, it's going to be what? What am I multiply by? Times 2, and then leave the answer in terms of pi. What is my answer? Now, I got a bunch of zeros in a row there. What do you think that is? Error. So what do you think the actual answer is? 3.15 pi, what? Units cubed. We're calculating volume. Does that make sense? Now, what did you actually find the volume of? Well, if you look at this region, and I'll make it a little bit smaller so you can see it. Here's my little region right here. We're rotating around the line x equals -2. So when you got that reverse image, it will show up way over on here on the other side. So you got a lot of big hole in the middle of this guy. So this is the reverse image. And then you've got, like I said, circular rotation on this guy. This is what you found the volume of. This 3.15 pi units cubed. Does that make sense? Did I lose you guys anywhere? Try this one. Now this was the problem that I came up with because when I first came up with these notes, I was using simple equations like, okay, y equals x to the 2/3, because you had to do a little bit of algebra to manipulate these equations back in the dishwasher method. But some of the faculty got so lackadaisical about these particular shell method versus dishwasher. We had several faculty that said, well, dishwasher, quote unquote, is so much easier to use, I'll just always use the dishwasher. Well, I said, well, you can't. I said, why not? We can always use the dishwasher. Well, at least on the problems that you came up with on these notes, and you're right, because I came up with easy equations that you can solve for x. So I came up with this one just to spite it. So here it is. Sketch and find the volume that is created by rotating the area bounded by the curves y equals x cubed minus 2x plus 4, y equals 0, x equals negative 2, and x equals 2, about the line x equals negative 3. Well, this one's a little more complicated, so this is where I'm going to actually use my graphing calculator to graph this guy. So clear this guy off. This will be x cubed minus 2x. It's a cube graph, so you know it's going to be a squiggle, plus 4. Now, y equals 0, I can graph. X equals negative 2, and x equals 2, I can graph. And I can graph x equals negative 3. It's this guy I want to graph, so I'm going to do a zoom 6. Zoom standard, negative 10 by 10 screen. So I got a nice cubic squiggle in this guy. I mean, that guy is not a one-to-one function. You can't solve for x in terms of y on this guy. You have to use a particular method. So let's analyze this. My function is in terms of x. We are rotating at about the line x equals negative 3. So when you draw this, and it looks like all I care about is between negative 2 and 2. So between negative 2 and 2, this thing looks like this. Here's negative 2, and here's 2. And so I'm kind of cutting this thing off. Here's that x equals negative 2. Here's x equals 2. And the other one was y equals 0. Y equals 0 is your x-axis here. So we're talking about this region right here. Does that make sense? Now, rotate this thing about the line x equals negative 3. X equals negative 3 is right here. So, my function, and I should label it, my function is y equals x cubed minus 2x plus 4. My function is in terms of x. I am rotating around something that is parallel to the y-axis. Opposite variables. X rotating around something to the y-axis. Does that make sense? What method will I use? This is a shell method problem. And volume is equal to 2 pi times the integral of the point radius times f of x top minus g of x bottom of my region dx from A to B. So this would be equal to 2 pi times the integral of the point radius. We'll put him in a second. But I always focus on the region first. The top, there's my region. The top part of this region is given by the equation x cubed minus 2x plus 4 minus the bottom part of this region is y equals 0 dx, and now I need to find my point radius. The point radius is from an arbitrary point inside my region, and because this is a dx formula, this will be an x arbitrary point. If I use the shell method version that has a dy, I would use a y point. This is an x point, and we want to know what the distance between that point is and the axis of rotation. So the point radius would be what? Right minus left. Arbitrary x point minus, in this case, negative 3, which makes it what? X plus 3. That's my point radius. Does that make sense? Now, what are my bounds? Very good. It's about not where it's going, it's where the region is originally. So that is between negative 2 and 2. Now, if I was going to do this particular problem by hand, minus 0 no one cares about, but I would literally have to FOIL this mess out, and then I could integrate each term. So it's still doable from an integral perspective, but just a pain. So I'm going to use the handy-dandy calculator on this guy. So go to my math number 9, integral between negative 2 and 2 of, parentheses, your point radius, x plus 3, times your function x cubed minus 2x plus 4 minus 0, okay, I'll just throw that one off, make it close parentheses, dx. And there's my answer. But what do I have to put on it? Times 2. Traditionally, we leave the answer in terms of pi, because otherwise it would just be an irrational mess there. So I'm going to leave it in terms of pi, but I do need to multiply it times 2. So I get an answer of volume is equal to 100.2666667 pi units cubed. Does that make sense? Now, what did you find the volume of? What is this 100.26667? And for those engineers that just want to know, you can multiply it times pi and actually see the amount. That's 314.9970234 units cubed of material here, volume. So, what did you just find the volume of? So, I'm going to put my little coordinate axis up here and redraw it again. So it looks like this. Okay? You rotate around the line x equals -3. So you get this reverse image on the rotation. And then you rotate it. So you got this nice circular aspect of this thing. What did you find the volume of? Oh, come on. You guys know this one. What does it look like? A what? An igloo? A funnel? Have you ever been in your mother's kitchen? Think mother's kitchen. A what? Well, yeah, I got a big hole in it. What? Bunt pan, right. Bunt pan. You guys know pound cakes and stuff? Thank you. So you have just found the volume of the bunt pan, the volume of a cake thing here. That's where I got the design from in the first place. Does that make sense, though? So, again, any kind of volume rotation, you can begin to actually see the images of these things. These are classic stuff in your mom's kitchen type thing here on making upside down pineapple cakes and stuff like that. So there you go. So, all right. So that's the big idea. And that calculator project I'm going to get you guys to do is really focusing on not just getting these formulas down. Because once you get these formulas down, you can go through these kind of problems literally in about 2 minutes, every problem. And that's what we're going to work on is speed. Recognizing the problem, plug into a formula, calculating it, move on to the next problem. Because there's a pattern to this stuff. And the calculator project, with the help of the calculator, is designed to get the pattern down. But on the calculator project, and I'll talk more about this after spring break and stuff when I really introduce it, but you guys are on the Friday class here. So what I really want is, I want you to state what method you're using, shell or disc washer method, on each one of the volume problems. Tell me, write up the formula for this thing. Draw a picture, write up the formula for calculating this particular volume, and then use your calculator to calculate it, just like we're doing in the notes. And again, the goal here is speed and process and catching a pattern, because after a while, this becomes trivial. You can just do this in your sleep. All right. The last section, and actually this was part of section 7.2 as we put all these notes together and stuff, is what we call non-rotational solids. Here we go. A three-dimensional solid has a shape that the base is in the region between the graphs of y equals x squared and y equals 16. Parallel cross sections with respect to the x-axis are squares. Find the volume of the solid. This section right here, in terms of the volume stuff, after a while, and again, especially with the help of the calculator project, that volume rotation on the, using a wood lathe or a metal lathe versus a potter's wheel type of spinning of rotation stuff, people get that down quick. People don't like this stuff, and I think it's because you actually have to outthink the problems. But there's a process to it. Here we go. First step one. You got to understand what's going on here. We got three-dimensional, so we're creating volume out of this guy, but we're looking at the base. The base is by the graphs of y equals x squared. I don't need a calculator for that. Y equals x squared is a classic parabola. Looks like this. And y equals 16. Y equals 16 is a horizontal line up here. So this is the base. Okay. Cross sections, here it goes. Cross sections with respect to the parallel cross sections with respect to the x-axis are squares. All right, let's classic English when you don't understand something. Break it into pieces. Parallel. Think about that for a second. Cross sections with respect to the x-axis. So parallel to the x-axis. What is parallel to the x-axis? Which way are you slicing this thing? See, that's the trick. Yeah, how are you going to slice this guy? You got it. Slicing it like this. Does that make sense? Parallel to the x-axis. So I'm making slices like this. Here it comes. If I'm slicing it horizontally, which axis am I actually cutting into? The y-axis. So these little blocks that I'm making are actually going to be delta y. That's going to be important in a second. Setting up the interval. Does that make sense? Parallel, so enjoy the words, parallel cross sections with respect to the x-axis. Because I'm either going to state it parallel with respect to the x-axis or maybe perpendicular to the x-axis. Perpendicular means I'm going to go cutting into the x-axis. That would make it a delta x problem. Which axis you're cutting into is going to be important. All right. But the aspect of this thing. Now, Dr. Taylor, that's a two-dimensional shape. You're absolutely right. But here it comes. This is the base. This is the piece of paper. And here it comes. Parallel cross sections with respect to the x-axis are squares. We're lifting out of the page, out of the paper, out of the base. You're lifting squares. Now, squares are, as I cut across, this thing's going to be this will be kind of a small square. And I'm trying to draw this thing three-dimensionally, so I'm trying to lift out of paper. So there'll be a square there. As I go up and pick a next line, this is going to be a bigger square that's coming out of the page. And over here, the top right at 16, this will be the biggest square of all. Does that make sense? And again, having art ability, which clearly I don't have, you're supposed to be able to see this vision of this object being lifted out of the page, and that actually has a volume. And you want to calculate this volume. Does that make sense? So here's the deal. And then I'm going to try to draw this thing a little bit better in a three-dimensional way. But here's the idea. To calculate volume, here is your formula for non-rotational solids. So it's classic calculus. We got another formula. It's the sum of the cross section areas times either delta x or delta y. And from this, you will write an integral out of it. All right. Now, you'll see why the people hate this section in just a second, because it makes you think. It's not going to be mindless working like we're trying to get these patterns down in the last rotation stuff here. After a while, you go, oh, the pattern, you can throw it in there. But this one, you're going to have to think the problem. So here's the deal. What cross sections do we have? The cross section area. What does that look like? What's my cross section area? It's this guy right here. I pulled him out, and I drew him in there, and what is he? He's a square, because he even mentioned the word square. What is the area of a square? Well, now if you're thinking rectangle, length times width. I'm thinking square, something special about a square. What's special about a square? And the sides are the same. So it's side by side or side square, because the length and the width are the same thing on a square. Cuts down on the number of variables. That's nice. So my formula here is going to be volume is equal to the sum of the side squared. And now I've got to pick which one's it going to be, delta x or delta y. It depends on the way you slice this guy. Because I sliced it and I the way I sliced it cut into the y-axis. Here's your y-axis here. when you slice it, and if you have to extend it over a little bit, when you slice it, you intersect the y-axis, that's going to be a delta y problem. If you cut it vertically, you're going to be intersecting the x-axis, that's going to be a delta x problem. Horizontal is a delta y problem, vertical is a delta x problem in the way you slice. So that slicing is important. So how are we slicing this guy? Parallel to the x-axis, which means we're what? We're cutting into the y-axis, so what kind of problem is this guy? Delta y. Does that make sense? Now, converting it to integral calculus. What does summation turn into? Integral. We'll work on this side square thing in just a second, but what does the delta y turn into? dy. So I'm now setting up my equation for my integral. You with me? But now, because you see that dy, I want to have y as my variable. But watch. Now, here's the deal. This is a side. And the side is actually, one of the sides is actually in your base, and it's typically going to be. The side is in the base. So what is the side? Watch this. Now, so as you look at this guy, and maybe my picture's throwing you off a little bit, so I'll look at this little guy down here. All right? We're talking about a side, but the sides are basically horizontal, and I'm moving, and so here's the side right here, and the y-axis splits it down the middle. When you move away from the y-axis, what direction are you going into? So I'm trying to convert this stuff into a variable, an x variable or a y variable. When I move away from the y-axis, what direction do I go? X. So this will be x on this side, and because of symmetry, it's x on this side. So what is the total distance of that side right there? 2x is going to be my side. Here it comes. Because I've got to analyze, and one of my sides, one of the sides is in the base, and now I'm analyzing my base of my structure here. But the y-axis split it down the middle. I moved x on one side, x on the other. So the total distance of an arbitrary side is 2x. Does that make sense? And so the area, which is side squared, would be 2x squared, which makes it what? What's 2x quantity squared? 4x squared. So now volume is going to be the integral of 4x squared dy. But I got a problem. What's my problem? I got an x in the middle of my integrating with respect to y. So I got to convert him over. And this is going to happen to you guys. So what do? The trick is the equation of the region that you got. What was that equation that made this base right down here? What was that equation again? Y equals x squared. That base equation that sets up your base is your conversion variable equation. Does that make sense? So, if y equals x squared based upon it was given, if I've got x squared, guess what I get to replace x squared with? Y, because y equals x squared. So, your area, which was 4x squared when you clean them up, will actually be the same thing as 4y. Does that make sense? So, x squared is equal to y, so that's a substitution aspect based upon giving the equation of the base here. So volume is equal to integral of 4y dy. And I've got my answer except for one thing. I got to have bounds. What's my variable? Which variable am I interested in on this one? Y. Look at the region. It would be defined over the region. Where are the y's going from? Well, you hit the origin down here, 0, and how was the top one? 16, up here at the top. So you're integrating from 0 to 16. Setting up these integrals. And so now integrate it. Integral of 4y would be 2y squared, evaluated from 0 to 16. Fundamental theorem of calculus, plug in top minus plug in bottom. That'll be 2 times 16 squared minus 2 times 0 squared. And 16 squared is 256 times 2 is 512. 512 what? Units, what now? Cube. You found volume. Now, I'm going to do my best to try to draw three-dimensionally what this thing looks like. Question. Well, first off, you needed to change it in terms of y. Why? That delta y that we're talking about, the slice, turned into a dy, which means y has to be the variable. Okay? But when I looked at my area, the area was based upon horizontal slicing, which means my variable was in terms of x. So when I created the area of the square, it was 4x squared. So I need to convert the x squared into a y. But the conversion factor is based upon the equation of the base. They gave me y equals x squared and y equals 16. Y equals x squared is where it's bending at, and that's the equation that converts your variables over. So x squared is actually equal to y. So I get to replace x squared with y, and that sets up my integral. Okay? But now, what does this thing actually look like? So on this one, I'm going to try to draw it. You know, this is what you guys will do in Calculus 3, so enjoy this. So I'm kind of turning it, flipping it down this way. This is your positive x-axis. Here's your y-axis. Here's the parabola. Here was the line, y equals 16. Okay, and this is your two-dimensional shape. And as I mentioned to you guys, the base, across the base, created squares. So you got a little small square there, come up here, make it a bigger square, come across here, make it a bigger square, come across here and make it a bigger square, come across here and make it a bigger square, come across here and make it a bigger square, and then right at 16 you got the biggest square of all. And you kind of connect the region down here with these lines, and that's actually what you found the volume of, this solid sticking out of the page that looks like squares because of the cross-section thing. Does that make sense? All right, try this one. A three-dimensional solid, and I want to show a difference. So here's my comparison between these two. A three-dimensional solid has a shape that a three-dimensional solid shape has a base that is a region between the graphs of y equals x squared and y equals 16. Parallel cross sections with respect to the y-axis are squares. Find the volume of the solid. So, once again, draw your base. Y equals x squared. Parabola. Y equals 16. It's the same base as the last problem, right? What's different? What's different is this. Parallel cross sections with respect to the y-axis are squares. So, parallel with respect to the y-axis. Parallel to the y-axis. How are we slicing this thing? Vertically or horizontally? Vertically. We're slicing it this way. Does that make sense? Parallel to the y-axis. And here, we're making squares. So there's going to be a small square here. There's going to be a bigger square here. Analyzing this piece will be a little bit bigger square. The biggest square would be in the middle, so forth and so on. Does that make sense? So these squares are sticking out of the page, but I turned them, and I'm slicing it this way. So again, this is what you need to know. Volume is always equal to the sum of the cross-section area. Okay? And we got to look at these slices. This is what we're talking about being cross-section. This is the cross-section. It's that square there. Times either delta x or delta y. So volume is equal to, again, the area, this cross-section area, is a square. And what was the formula for the area of a square? Side squared, right? Side by side, side squared. We need to analyze a side. But now, volume is going to be the sum of this cross-sectional area, which is s squared times what? Which one of these two guys? Is it a delta x problem or is it a delta y problem? Delta x. The reason why, even though the regions up here, you're making slices that actually cut into the x-axis, this is a delta x problem. Because it's vertical, you're going to cut delta x. It'll be a delta x problem. When it's horizontal slices, that'll be a delta y problem. Your setup. But now, to create this guy, converting this to integral calculus, this will be the integral of side squared, but this time it's going to be dx. But I need to calculate the area, this side. What exactly is a side? This is a side right here. It is a distance. And because it's a distance, and on this one, I've got a distinct top and I've got a distinct bottom. So what is the distance of this section right here? What's on top? 16. minus what's on bottom. This is the equation of y equals x squared is the parabola. Because I'm going vertical, I have a distinct top, bottom. It's top minus bottom. And the bottom is x squared. Does that make sense? Over here, I had rights and lefts, but this equation was in terms of y, so I could actually convert this thing over if I wanted to and do right minus left on this guy, but then I would actually have to solve for x. That would be the square root of y minus the square root of y, and basically top minus bottom, and you actually get the exact same equation. Square root of y minus, this is negative square root of y on this side. Square root of y minus negative square root of y would be the 2 times the square root of y, then you square and you end up getting 4y. You can do it that way as well. Top minus bottom or right minus left. It's still coming back to haunt us. So this one is, I have a distinct top function, 16, distinct bottom function, which is y equals x squared, 16 minus x squared. So volume is going to be the integral of 16 minus x squared, but it's area, so what you got to do, that was the side, you got to square it, dx. One last thing though, what's my bounds? It is from where? You said it. And how did you get it? This is dx on x number. So x squared meets up at 16. So x squared equals 16. So x is equal to officially plus or minus 4. So they meet up here over at negative 4 and over here at positive 4. So you're integrating from negative 4 to positive 4. You got to use x numbers on the bounds. Does that make sense? Now I could integrate this thing by hand, but I would have to fold this guy out. So quickly, let's just integrate it on the calculator. Math number 9, integral from negative 4 to 4, and parentheses 16 minus x squared, close parentheses squared, dx. And what do I get? I get 1,092.26667, or for you math fraction fans, this thing should convert to a fraction. 2.6666. I need more decimals to get it. 7 math fraction 4/5. You can also say this is 1,092 and 4/5. What? Units cubed. But got a question for you. Couple of things here. Number one, I wanted you to notice here that comparing between the two problems here, the fact of the matter is you did not get the same answer. You know why you didn't get the same answer? It ain't the same picture. Slicing it one way is different from slicing it another in terms of volume. This had longer strokes, which would make bigger squares. Bigger squares makes bigger areas. Does that make sense? There's a classic setup for this stuff, and these things can be rather painful, but remember, top minus bottom or right minus left is how you get these equations. We'll study more of this after spring break. Enjoy your spring break, study hard, and take a look at that calculator project. It's out there for you.